Now let's change gears. Instead of talk about phototransduction, let's talk about light-dark adaptation. So one of the major features about the visual system is that it is not only very sensitive to light, but also be able to operate over a very large dynamic range. So for example, if you're in a dark environment and suddenly you move to an environment with a lot of light, after a few minutes, your visual system adapts and somehow your visual system is able to detect shape and color of objects by decreasing the gain of your visual system. Likewise, if you're moving from a very bright environment to a very dark environment. So for example, if you're in an outside environment and then you move to a very dark movie theater, uh, in the first few minutes it takes a while for you to find the chairs and so on. But then after several minutes, now your visual system increased the gain and now you're able to see better even with very dim levels of light. So this intrinsic mechanisms that are present in the visual system is what we call light-dark adaptation, and both rods and cones adapt. So both rods and cones become less sensitive as light levels increase or become more sensitive as the light levels decrease. This mechanism of light-dark adaptation is very important because it allows the visual system to work a very large dynamic range, and this figure shows luminance levels at very dim light levels, about starlight or less, and all the way to very bright sunlight. So this is about 14 orders in magnitude, and the visual system is able to operate over this many orders of magnitude. Um, this type of vision that operates at very low levels of light we call scotopic type of vision, and is mostly mediated by rods, while the type of vision mediated by cones with more intense levels of light that we call photopic, and mesopic would be the levels of light in which both rods and cones are able to operate. So light dark adaptation allows the visual system to operate within the dynamic range if for example in a Minneapolis day, or if you go to indoor lighting by 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 adjusting the gain of the visual system. And so again, this change of the gain of the visual system happen at many different levels along the visual pathway. For example, it happens at the level of photoreceptors, it happens at the level of horizontal cells, it happens at the levels of central pathways, but the consensus is that the photoreceptors have a very large contribution in terms of light-dark adaptation. When we think about light-dark adaptation in photoreceptors, the major molecule here is calcium. And calcium is an important molecule because cyclic GMP gated channels allow the influx of cations, but also it allows the influx of calcium. So when in the dark, when the cyclic GMP gated channels have a relatively high open probability, calcium influx is relatively high, and therefore the intracellular levels of calcium in photoreceptors is relatively high. While when the photoreceptors are exposed to light, and psycho-GMP levels fall and these channels close, then this calcium influx is diminished, and therefore the intracellular levels of calcium decrease. Now, calcium has many different effects in photoreceptors. First of all, low levels of calcium is actually increase the activity of the guanylyl cyclase inside of these cells. This increase of the levels of guanylyl cyclase will increase the levels of psycho-GMP and therefore will reopen these channels. So these channels that when the photoreceptors are exposed to very bright light, this decrease of calcium will restore the levels of psycho-GMP that will lead to reopening of a fraction of these channels, and therefore restore the sensitivity to light for these photoreceptors. Some other actions of calcium are also listed in this slide. So for example, low calcium increases a low calcium increased activity of rhodopsin kinase, and that also leads to faster inactivation of rhodopsin. And also low calcium increased the affinity of psycho-GMP channels for psycho-GMP, and all these actions of low calcium will ultimately lead to the reopening of the psycho-GMP gated channels, and that will allow the cells to respond to light even at very high levels of light. The molecular mechanisms that underlie this activation of guanylate cyclase is shown here in this slide, where you can see that the guanylate cyclase has several different domains, and is bound to another protein that's called guanylate cyclase activating protein, that when calcium is bound to guanylate cyclase activating protein, the guanylate cyclase is inactive, while when calcium dissociates from the guanylate cyclase activating protein, now the guanylate cyclase is active. So when the calcium levels inside of the cells are relatively low, in this scenario here, then there is a production of psycho-GMP, so there is high levels of psycho-GMP inside of these cells. Another important consideration about light-dark adaptation pertains to this what we call the visual cycle. The visual cycle refers to this cycling of the chromophore along the photoreceptors to the retinal pigment epithelial cells. As we said before, if you move from a very dark environment, from a very bright environment to a very dark environment, it takes several minutes to restore the light sensitivity for your photoreceptors, and that has to do with of this visual cycle. So here it is shown schematically some of the enzymes involved in this visual cycle. Here are some of the enzymes found in rod outer segment, and you can see that 11-cis retinal that's bound to rhodopsin when activated by light, and then is isomerized to ultrans retinal. This ultrans retinal that's bound to rhodopsin will dissociate from rhodopsin, and this ultrans retinal then is reduced by a specific enzyme to ultrans retinol, and then ultrans retinol can diffuse to these retinal pigment epithelial cells that makes close contact to these photoreceptors. Ultrans retinol then is transformed back to 11-cis retinal by the action of those three different enzymes. One that's involved in esterification of ultrans retinol, another involved in the isomerization, and finally another enzyme that oxidize the 11th retinol to 11th retinol. And then the 11th retinol can diffuse back to the rod outer segments and then join or covalently bind to rhodopsin and then become a chromophore that's sensitive to light. This is called the classical visual cycle, and when the photoreceptors are exposed to very bright light, it takes several minutes to restore uh, the 11th retinal back to these photoreceptors, and that's why it takes several minutes for you to restore the photosensitivity of photoreceptors when you move from a very bright light to a very dark environment. So this is a dark adaptation step. So again, this is the classical visual cycle. It involves those different enzymes, and the main purpose of this classical visual cycle is to regenerate 11th retinal from ultrons retinal. Rod photoreceptors make use of this classical visual cycle to restore 11th retinal. And in the past few years, also we learned that cones can make use of additional visual cycle that involve glial cells in the retina. These glial cells in the retina is named Miller cells, and this Miller cells are able to restore 11th retinal to cones, and cones are able to use 11th retinal to 11th retinal to restore the chromophore to this coneopsins. So that explains in part on why cones are able to operate even at very high light intensities, while rods can make use of only this very limited slow visual cycle. The cones can make use of this additional visual cycle that actually operate at much faster rates, so it can sustain regeneration of 11th retinal at much higher rates in cones. Why do we need rods and cones? We know now that rods are less noisy than cones. Cones are much noisier than rods, but one of the major features of cones is that it's very difficult to completely bleach these cells with light. So it's very difficult to saturate these cones with light, and one of the major reasons is again is that the cones can make use of that additional visual cycle that involve the Miller cells. So here's another exercise. The following are current traces from salamander photoreceptor in dissociate and intact retina. Here in A is dissociate cones, so the photoresponse of dissociate cones. Cones recorded for intact retina, and rods for intact retinas. And here are the different photocurrents elicited by flash of light of increased intensities. And what you can see here is that for a dark adapted retina, in dissociate cones, you can bleach with light, and they can restore light sensitivity of these isolated cones by providing some 11th retinal. Now, the photoresponse of these cones is quite different in the intact retina. It's very difficult to bleach with light the photoresponse of cones, as you can see in dark adapted conditions, and even bleaching with light, you can get relatively intact responses. Now, rods for intact retina, on the other hand, exhibit the responses, photoresponses that can be bleached quite easily with light. So, in this case, explain the differential effects of light bleaching on rods and cones, and what would we expect result in eye cups. Eye cups is a preparation with intact retinas attached to the retinal pigment epithelium. What you should know from this lecture, you should have a pretty good idea about how rods and cones are able to transduce photons of light to electrical signals. You should have a good knowledge about the biochemical machinery that allows rods to maximize photon capture in the discs. You should be able to explain this amplification cascade in photoreceptors that allows photon capture to be amplified to a large response in the cells. Be able to explain not in terms of specific subunits or so on, but the general idea about some of the major difference between rods and cones, and have idea about light dark adaptation and why it's relevant for the visual system. And finally, the major pathways for light dark adaptation in photoreceptors, and the classical and the cone visual cycle, and its relevance for light dark adaptation.